All right, let's get started. So, good afternoon, everyone. Welcome to the third week's interactive session of the course Viscous Fluid Flow. Uh, let's quickly recapitulate what we learned in the second week. And in the meantime, if someone else has joined, they can go through it. So, in the previous week, we basically looked at the Navier-Stokes equation, which basically appears in your screen as something like this. So we saw that we tried to understand what were the different terms that involved in the NS equations. Just 1 second, guys. I'll make sure if the recording is in progress or not. Yeah, recording is there. Okay. Okay, so in the previous week, I believe I am audible. Can you just let me know if I'm audible or not? Okay, thank you. Thank you, IOC. So in the previous week, okay, thank you. We basically looked at the different terms involving in the Navier-Stokes equation. So we saw the term on the left-hand side, which basically denotes the force due to inertia. Then we said that basically this equates to some other terms which involve the pressure gradient, the viscous force, and the body force. So we physically looked into some special cases that involve, before that we saw that primarily the Navier-Stokes equation coupled with the continuity equation involves calculating three unknowns, and we have three equations since the NS equation itself is a vector equation. So in the three-dimensional system, we extract three equation out of this vector equation, and then one more equation comes out from the continuity equation. So it involves calculating three unknowns using, sorry, four sets of unknowns using four equations. So basically it's a bounded problem that we are essentially trying to solve for. Then again, we looked at certain special cases. What happens when there is a static fluid? We eventually saw that it leads to nothing but the law of hydrostatics, which is basically that the pressure gradient is balanced by the gravity. Then we looked into the special case of a fluid which we call as the inviscid fluid. Basically, the dynamic viscosity is equals to 0, and we got the infamous Euler's equation. And if we integrate the Euler's equation along a straight line, keeping in mind that we are dealing in a steady problem, we found out that it leads to nothing but the Bernoulli's equation. Then we solved certain examples involving the plane Poiseuille flow and the Couette flow problem. And I like stressed on the fact that if we have a governing equation which is linear, which basically is some so the equation that we saw in the last week, so that's a linear equation, as you can see, because both of these terms are linear in nature. So the idea is that if we have a linear governing equations, and of course the boundary conditions are also linear, then the solution of the entire problem is basically a linear superposition of the solution of two simpler problems. For instance, we looked at a problem where the upper plate was moving with some u0, and also there is an axial pressure gradient that has been applied in one direction. So the solution that we got is a combination of the Couette flow velocity profile plus the velocity profile that would be generated if the upper plate is fixed and the whole fluid only moves with the help of a pressure gradient. So this is something that we saw. So the final answer basically appeared something like this, and then we discussed about this linearity principle. We also evaluated the volume flow rate, and this is something that doesn't need so much of an explanation. And then we looked into a problem which basically involves calculating the shear stress. Okay, so this was something that we did in the last week. So before starting this week's before starting this week's problem, I will stop here for, let's say, 2-3 minutes or maybe 5 minutes. You can if you have any doubts on the previous week's lecture series, or like the problems that we solved, or this week's lecture series, in fact, you can let me know. I would wait for a couple of time, or else we will start off with this week's session. Okay, all right. So I believe like you don't have any doubts till yet. So please let me know if you have any, and feel free to like stop me at any point of time. We will begin our sums like discussing our problems today. So today, as I said, we saw one problem, but we didn't explicitly solve it. That is something known as the flow near a moving belt, and we will actually try to see what will be the velocity profile when there is a belt which is basically moving with a fixed velocity, of course in an inertial frame of reference. And then if there is a fluid which is basically adjacent, which basically sticks to the belt, and when the belt moves, the adjacent fluid also tends to move, and then our objective is to calculate the velocity profile of that nearby fluid or nearby chunk of fluid. This is the first problem that we'll see, and then we'll move ahead to a special class of problems which involves calculating the velocity field when there is a fully developed, hydrodynamically fully developed flow in a pipe of radius, let's say r, and these problems are known as the Hagen-Poiseuille problem. We will see sums associated with the Hagen-Poiseuille problem, and like if time permits, we will also look into a simple case of a problem where there are two cylinders which are concentrically rotating with respect to one another with some known angular velocity. And then if that is the case, we will try to see what will be the flow field associated with the rotation of those cylinders, which is basically, so this problem is basically known as the so this is, so actually this is known as the flow between rotating cylinders, but they are also given special name. I could not recall the name now, but if I remember, I will let you know in the, like, if I can recall exactly what they are exactly called. So I think they are known as Taylor Quate flow or something like this. I don't exactly remember the name or the jargon, but yeah, that involves just calculating the flow field between two rotating cylinders. So this is the agenda. So let's get started with the first problem. So as I said, the first problem, so this is something that we saw in the last class. However, like I just set up the problem and I said that we will be solving it in the next week. So here it is. So as you can see, there is a belt which is basically indicated by this black dash line. So this belt moves with a known velocity u naught, and when the belt moves, usually because of the no slip boundary condition, the layer of fluid which is attached to this belt also moves with the same velocity u naught. This is typically due to the no slip boundary condition, as you guys know. Then, due to viscosity, this uh, adjacent layer of fluid adhering to the belt also pulls the fluid around it. Okay. Then what happens is the fluid tends to move, and it's like the belt drags the fluid along it. However, because of the action of gravity, there is also a gravitational force which is acting in the downward direction. So the idea is, if this is the physical picture, okay, if this is the physical picture, and I'm assuming that the belt is of infinitely large length such that the end effects are neglected, and if this is the picture, then the idea is to calculate the velocity profile of this physical paradigm, as you can see. So I hope the physical picture is clear. Yeah. So I'll write one more thing that so the idea behind this fully developed assumption here is that the belt is of infinitely long. Yeah, so belt is basically infinitely long, such that the end effects are basically neglected, or you can say that the x direction. So, or you can say that in the x direction, the gradients will basically become to be equals to 0. This is the idea behind the fully developed condition. So, if this is the case, so what I hope this is clear to you. So, what we need to find out is, first of all, we need to evaluate what are the boundary conditions at y equals to 0 and at y equals to h. H is basically the thickness of the fluid. So here this H is basically the thickness of the fluid that is being stuck with the belt. Okay. So we are asked to find out the boundary conditions at y equal to 0 and y equal to h. And after like evaluating these boundary conditions, let's then go ahead and find out the velocity profile. Okay. So again, this is a planar problem, as you can see. And we will now start off with the assumptions. So before so again, we will do this very systematically, just like how we did in the previous week. So before starting, I would stop here again for some time. Can you like tell me how do we like start off with the problem? So what's the basic step that we do here? Like, so what's the first basic step that we do when we solve these kinds of problem? If you feel to answer or if you wish to answer, you can let me know. So before that, just before like you say your answer, I will first write down the assumptions which are basically important. And these assumptions actually lead to simplifying the NS equation that we will solve here. So the first assumption is that we will consider the fluid to be Newtonian, of course. So it's a Newtonian fluid. The second assumption, of course, is that we are dealing with a steady state problem. Okay. The third assumption is that so this is something that I have already said, that it's a fully developed flow, which means that the end effects of the belts, so that which means that the belt is so long that we are just looking into. So I believe you have got the idea of the fully developed condition. But this means that the belt is so long that its end effects, so whatever the physics that happens towards the beginning at the end of the belt, we are not taking into consideration. And this means we are only interested in some middle portion of the belt. And this is where we are basically looking into the physics of the problem. Okay. This is the idea behind the fully developed condition. So basically, it's a fully developed flow. So this means that and so I'll just write it. It means that the beginning and oops, sorry, and the end effects are neglected. All right. Then what do we have? Okay, then we can also assume one more assumption, which is basically the 1D flow assumptions, which means that, so the 1D flow assumptions here means that, so whenever the belt moves, the velocity, the streamlines will be along the x direction only. This means that the streamlines again are nearly parallel and we don't have a flow in the y direction. This is what the 1D assumption suggests. And in practical cases, the streamlines are never like that, never like exactly parallel in the x direction, but you can say they are nearly parallel. So in spirit, if we are trying to like develop a theory out of it, we can assume that if even if they are nearly parallel, even if they are nearly parallel, we can assume that they are exactly parallel, and we consider the flow to be just one dimensional, which means that the flow is now in only in the x direction. Where, as I have already said, the x direction in this case is along this axis, this red axis, as you can see. Okay. So we can, so this is basically the 1D flow assumption. All right. So I have listed down the assumptions here. I have listed down the assumptions. So now can you tell me how do we start off the problem? So now let's start off with the solution. What's the first step do we do? If you recall the previous week's class or at least the lecture series. So what's the first step that we do now? Can you tell me what equation do we start off? What's the first equation
Mass
now?
conservation.
Yeah, exactly. So we start off with the mass conservation or the continuity equation, as you have rightly pointed out. So since we already, so this is the repetition of the some of the previous week's problem. I'll solve this problem relatively fast, such that we understand the physics as well as try to cover more problems today. So we start off with the mass conservation, as you have rightly pointed out, or this is known as the continuity equation. So when we apply the continuity equation here, so what is the continuity equation? It is just del u by del x plus del v by del y is equals to 0. Because of course we are now looking at a planar problem where there is no z direction. Okay. Now the 1D flow assumption again suggests that the y directional velocity is of course 0. This means that it's a 1D flow, and this means that del u by del x is equals to 0, which again suggests, as we have also seen in the last week, that u is not a function of x. This means, therefore, u is just a function of y only. Okay. Again, this suggests that we are now dealing in a 1D flow problem, and we now have a hint that we can convert the like complicated PDE, because the NS equation is basically PDE, into a ODE, because of the fact that this u is now just a function of y. Okay. So next, what do we do? What's the next step? Can you tell me?
X momentum equation.
Yes. So we apply the x momentum equation. So we apply the x momentum. All right. So when we apply the x momentum, let's write what basically is the x momentum. So on the left hand side, we have the inertia term, which is basically what? It's basically the total, it's the material derivative of basically. So if you recall, it's basically the material derivative of the velocity v. So if I split that material derivative, it becomes what? It becomes something like this. The temporal term, which is del u by del t, plus u times del v by del x, plus v times del, sorry, this is u, so this del u by del y, okay, and this becomes equals to the pressure gradient, which is minus of del p by del x plus the dynamic viscosity mu times del square u by del x square plus del squared u by del y square minus rho g. Okay, so now we'll invoke all the assumptions that we have listed down. So the first assumption, the steady assumption, suggests that the temporal term will of course go to zero. The fully developed assumption suggests us that del u by del x, so u is not a function of x. So this is from the continuity equation as we have seen. Again, this is very familiar to the last week's problem. So I hope you can relate these things very quickly. Since the flow is one dimensional, this v becomes equals to 0. Okay, and then we do not have a pressure gradient now in the x direction. Okay, this means del p by del x will also go up to go to equals to 0. Del square u by del x square is also 0, because that is basically because since del u by del x is 0, its derivative with respect to x will obviously be equals to 0. So this means we get a balance now. So this means we now get a balance between mu times. So I hope the assumptions are clear. I believe I do not need to write them explicitly now. However, I'll just state these things here. So this is the steady state assumption. This is basically what del u by del x is basically, this comes from the continuity equation. This comes from the fact that it's a 1D flow. This is 0 because this is 0 because the physical problem says that there is no pressure gradient. And again, since del u by del x is 0, this means that del square u by del x square will also has to be equal to 0. So we just end up getting this term, which is mu times del square u by del y square equals to rho times g. And since u is just a function of y, I can just replace the partial derivative with the ordinary derivative, which is d square u by dy square is just equals to g. So now from this, we know that we need to integrate it, but I'm now asking you a like asking you a physical question here, that from this ODE and from the picture as it appears, can you tell me what? So as we all know, the NS sequencer equation is basically a force balance. Okay, it's a conservation of momentum, and since momentum is conserved, there has to be balance between the forces. So can you now tell me from this equation, what are the forces that are being balanced here? Yeah, go ahead.
Viscous and gravitational force.
Yes, exactly. So exactly. So the viscous drag that the viscous drag that the belt is exerting on the fluid is in the upward direction. Okay, that is because the fluid exerts a force on the belt in this direction, and that's why the belt exerts this force on the fluid in the upward direction. So if I take this fluid to be as my control volume, then the viscous drag is in this direction. Okay, and the gravitational force is in this direction. So there is a balance between, so there is a balance actually between this gravitational force and the viscous drag. Of course, this is something that you need to visualize, because now the control volume is the fluid and not the belt. Okay, so the direction of the forces are very important here. So this is basically the control volume that we are seeing. Again, I will repeat. If I look at the belt, then the drag that the fluid exerts on the belt is of course is in this direction. However, we are not looking the belt as a control volume. So since we are looking the fluid as a control volume, we need to see what are the forces that are being exerted on the fluid. And the force that a belt exerts on the fluid by Newton's third law is will obviously be in this direction, and it is balanced by the gravitational force on the fluid. I hope this physical force balance is clear, which is of course we get from the equation, as you can see. That is simply because the sign, so as you can see, the sign of the viscous force and the sign of the gravitational force are opposite in nature. Okay, So if this is clear, then the rest is just mathematics, as you know. So we'll just do that quickly. So we need, so the next step is just integrating. We'll just integrate. So we'll just integrate with respect, of course, with respect to y. And if we do that, it just becomes mu times du by dy is equals to rho g. This becomes what? 1 second. We can do this, like we can do this problem very quickly. Okay, that's fine. So it's mu times du by dy. This becomes rho gy plus c1, of course. That is simply because we are integrating this with respect to y. Okay, and then again, if we do the second integration, again with respect to y, what we will get is we will get mu times. Okay, let's just do one thing. Let's first of all divide this equation by mu. So this becomes what? This becomes u times du by dy equals to rho g by mu times y plus, since mu is a constant, c1 by mu will also be a constant, which we are again writing as c1. So this becomes just some c1. Okay, I hope this is clear, because if we divide this equation by mu, okay, this becomes what? This becomes c1 by mu. Again, c1 is an arbitrary constant, so c1 by mu is also an arbitrary constant, and without the loss of generality, we are writing it as c1. And then what we'll do is we will integrate this then with respect to y. Okay, we'll integrate this with respect to y, and then what we will get is the velocity profile q as a function of y is equal to what we will get. So we will get rho g by 2 mu y square plus c1y plus c2. All right. So this is the boundary. Sorry, this is the velocity profile that we get. Now here comes the first thing, the first question that they're asking. Okay. So what will be the boundary conditions now? Can you tell me what will be the boundary conditions? So first of all, how many boundary conditions do we require to solve this problem? Can you tell me?
2.
Yeah, two boundary conditions. So if I require two boundary conditions, can you tell me now what will be the boundary conditions? Let's say now, first of all, let's say we're looking at y equals to 0. So what is u at y equals to 0?
U equal to U naught.
U naught, yeah. And why is it so? Why is it so?
Belt is moving upward with me.
Yes, but this is known as the no slip condition, right?
No slip
Yeah,
condition.
exactly. So this is the no slip condition. Okay. Okay. Now, can you tell me what is basically u at y equals to h?
That is all 0.
That is 0. Why? That is because the fluid, so it's the very nature of the fluid that, okay. So it's the very nature of the fluid that near the belt, since the belt is moving, okay, this will basically move with the velocity u naught. And here, there is no any other forces that is being acting on the fluid apart from the gravity. So at a far field, which is basically when you are moving far away from the belt, the fluid obviously has to come to rest. Okay, so this is again by the nature of the fluid that is moving and the action of the belt which is being acting on the fluid. Okay, so this means that I hope this is clear. So at y equal to h, this has to be equals to 0. So if we now apply these two boundary conditions, which are equation 1a and let's say b, in 1, if we apply this in 1, I would I will not solve the math here. That is because it's just repetition of what we did. We will see that. So what we will see that we will see C2 to be equals to U naught, and C1 basically comes out to be minus rho G by mu times H by 2 minus U naught by H. Again, this is very simple and you can verify it at your home or whenever you do. These are the two constants. So if I plug in this constant in the so these are the two constants that we solve for from the two boundary condition. So if I now plug in these two constants in this equation, the velocity profile that you get is simply something like this. So it is just u as a function of y. This is basically rho g. So I'll just write the velocity profile. You can verify it by yourself. This rho g by mu times y square by 2 minus hy by 2 plus u naught times 1 minus y by h. So this is again the velocity profile. Now The math is fine. Okay, the math says that this is the velocity profile. Now, can you relate this problem with something that I have already told you like half an hour ago, or something that we did in the last week? Can you relate this? So, can you relate this velocity profile, and can you tell me some conclusions from this?
Superposition
Yeah,
of
exactly,
tokens.
exactly, exactly. IUC is right. So, as you can observe, see, this is the flow field that is generated because of the gravity. It's because of the nature of the gravitational force that is acting on the chunk of fluid. And this is the contribution from this term. And this is the term which is basically the term which causes the fluid to move along with the belt. And since I have repeatedly said the governing equation, which is basically what? Which is basically this, is linear. This is again the superposition of the motion of the fluid, which is caused by the movement of the belt in the upward direction, plus the motion of the fluid, which is basically due to its own weight, which is the gravity. Okay, and this is basically a balance between these two forces, and that's why it comes as a two terms in the velocity profile, which of course you have understood right now very clearly. Okay, so this is the resultant velocity profile that the question has what the question asked us. And okay, so I believe you have understood this problem because your answer says you have understood the problem. So we will now move ahead. However, still, like I would wait here for like a couple of minutes, maybe. If you have any doubt, you can ask me, or I'll move. I will begin the second problem. So I'll state the second problem. But if you have any doubts for the previous problems, you can let me know. Of course, like before beginning this, I'd be happy to wait for a couple of minutes. Okay, let's get started. So when I stated the agenda for the second week's problem, I quoted a term which is basically the Hagen Poiseuille flow. So Hagen Poiseuille flow is very similar to the plane Poiseuille flow. So in the plane Poiseuille flow, the geometry are the plane plates and the fluid is moving in between. In the Hagen Poiseuille flow, of course, instead of plates, we have a pipe, which basically appears something like this. The water basically moves, or water or whatever fluid that we are considering. We will assume it's a Newtonian fluid as of now. And this Newtonian fluid basically moves through this pipe. Okay, and as you can see, so basically what happens is, like initially this there is a developing region of this flow which I will not discuss now. When we will basically go into the boundary layer and so on and so forth, we will see what is basically a developing region and a fully developed region. But we are now assuming that the pipe is so long that we are now considering a region which neglects the beginning and the end effects of the pipe. And in that region, this is typically known as the hydrodynamically fully developed region. We are doing the analysis, and this class of flows in the hydrodynamically fully developed region is known as Hagen Poiseuille flow. As you know, can you tell me what is the nature of the velocity profile in Hagen Poiseuille flow? This is something that you have learned in this week's lecture. Can you tell me what is the nature of the velocity profile?
Parabolic.
Exactly, parabolic. That is parabolic, provided that the flow is laminar. That is something that you need to understand. If the flow is turbulent, we lose that parabolic velocity profile. Uh, then we get a different set of velocity profile. But in case of these laminar conditions, in the region where the flow is fully developed, we know that the velocity profile is parabolic. And you have done the derivation, of course, in this week's lecture series. Okay. So given you know that information, let's try to understand this problem. So the problem says that there is a flow of water which is basically generated by an applied pressure gradient. However, the magnitude of the pressure gradient is for us to evaluate. Okay. And it is given that we are in the fully developed conditions. Although I have not stated this, the flow is laminar in nature. The diameter of the pipe is given to be 25 mm. The mass flow rate is given to be 0.01 kg per second. And this temperature, of course, you don't need to use this temperature, but it's given that we are in the room temperature setup, that it's around 25 degrees Celsius. And this is a pipe, so now we need to like use the cylindrical coordinate system, and this is the z direction and this is the r direction, and the theta direction will of course be, so it's a revolution. So if there's a revolution around the z direction, that will basically be the theta direction. I think you understand that if there's a revolution around this will be the theta direction. Okay, if this is the case, what they're asking is, they're asking us to calculate the maximum velocity of water. Okay, this is the first thing that they're asking. What will be the maximum velocity and the pressure gradient, which is basically driving the flow. Okay, so this dp by dz is basically driving the flow, but this is non a priori. This is not known a priori, and this is something that they are asking us to evaluate. Okay, so think about, so see the problem first, think about it, and then can you tell me how do we go on and evaluate this? And these are the given values that they have already said to us, that the diameter is known, the mass flow rate is known, and temperature, although we don't need to use it explicitly, is also given to us. Based on this, can you think about it, and can you tell me like how do we evaluate the maximum velocity here? Remember, the maximum velocity is not the average velocity in case of this Hagen Poiseuille flow, because you already said that the velocity profile would be parabolic in nature. So at these 2 points, the velocity of course would be 0 due to the no slip boundary condition, and the maximum velocity, if you closely observe, will be at the center line because it's a parabola. Okay, I will wait here, and I want your response in answering this because it's not that tough of a problem. So So yeah, think about this. You can draw the physical setup, and then if you have any ideas on how to, of course, I will solve that problem for you. But if you have any ideas on how to solve this, you can tell me or let me know.
Uh,
Yeah, go
Hello.
ahead. Yeah, go ahead.
Okay. First, continuity equation
Okay.
will apply,
Okay.
followed by momentum equation in
Okay.
z
Yeah.
direction. We'll get
True.
the velocity profile, and then
True.
from
True.
that velocity profile, you can have an idea of maximum center line
Yes.
velocity.
Yes. From that velocity profile. Okay. So maybe we can have a velocity profile which will basically, so now since we are in a cylindrical coordinate, we mean that we will now evaluate the z direction velocity, right? So let's say the z direction velocity is a function of r, we know. Okay, so this is something that we know. So if we know that, we will get the maximum velocity. That is also fine. So let's say we now have a maximum velocity, and that is known to us. But from the maximum velocity, like, okay, like I will tell you. So your steps are right. I'm telling you a priori that UZ, the velocity profile, as you have also solved. Can you? So I think you have solved this in your class. So the velocity profile basically comes something like this, which is basically 1 by 4 mu dp dz times r square minus r square. Okay. So based on your steps only, I'm telling you that the velocity profile is this. Now you also told me that the maximum velocity would be at r equals to 0. That's fine. Then u max is basically 1 upon 4 mu dp dz times the capital R square, which is basically the radius of the pipe. And since the diameter is given, we know what's the radius of the pipe. However, as you can see, this dp dz is unknown, right?
Yeah, mass flow rate will use
Exactly,
to
exactly,
compute.
exactly, exactly. So that's the idea. So your answer is absolutely right. Uh, so I will not show the steps here, but as you said, we will start off with the continuity equation. Okay, then use the z momentum equation, because here we will use all those assumptions. And as you can see, the fluid velocity will be in this uz, which will basically be the fluid velocity along the z direction. And if we invoke the 1D flow assumption, and the fact that there is no cross stream, there is no flow, and that the streamlines are along the z direction and there is no flow in the r direction, we will see that uz will just be a function of r. So this is something you have derived this equation. Okay, you have derived this equation in this class. That's why we will not derive it. However, as you have rightly said, okay, maybe I will do this nicely. Where it is. Maybe I'll start it systematically. So yeah, So yeah, what I was saying is, as RUC rightly pointed out, we will get a velocity profile which is basically something like this. So this is be UZ, which will be a function of R, and it is 1/4 mu times the unknown pressure gradient dP dz into R square minus R square. All right. Now, since we know that the velocity profile is a parabola, and if these two are the extreme ends of the pipe, okay, if these two are the extreme ends of the pipe, then I know that the velocity here and the velocity here would be 0, which means that the velocity profile would look basically something like this, and the maximum velocity would occur at the center line, that is at r equals to 0. Okay, because this is our r direction, and this is u max. So if we put r equals to 0 here, if we put r equals to 0 in this equation, we will get u max, which is basically uz at r equals to 0, and this would be equal to minus 1/4 mu times of dp dz times capital R square. Okay, but the thing is, we don't know. So the thing is, we don't know what is Umax, we don't know what is Umax, and we don't know what is dp dz. That's why we require one more set of equation, and that will come from the fact that the mass flow rate is known, as you have rightly pointed out. So if you write the definition of mass flow rate, m dot, which is basically the mass flow rate of water through the pipe, this is basically what it is, rho times, it is rho times the area times. However, can you tell me now what will be this velocity? Will this be the maximum velocity or something else? Can you tell me? That is the second question actually I wish to ask. So now what will be this velocity? Yes, rightly the mass flow rate is known, but now will this velocity, so my question is, will this velocity be u max, or this will be something else? Yeah, can you tell me now? Think about it. Just think about it. Will that be u max? Is mass flow rate calculated on the basis of the maximum velocity, or it is calculated on something else? Okay, I'll give you a hint. So in last week when we calculated the volume flow rate, uh, so remember when we calculated the volume flow rate, we integrated the velocity profile along the y direction, and that gave us, so when we integrate the velocity profile along the y direction, we got something which is known as the average velocity, and then from that average velocity we calculated the volume flow rate. Okay, which is basically the area times the average velocity. So when the mass flow rate also and rho times the volume flow rate is the mass flow rate, which is basically given to us. So this velocity will always have to be the average velocity and not the maximum velocity. Okay, because mass flow rate is a constant quantity. Okay, and u max, so the idea is the mass flow rate should not vary along y. That's the idea. So if you are considering the mass flow rate, which is basically an average quantity, we also need to calculate the velocity which is corresponding to that average quantity, which is basically the average velocity. All right. Did you get the idea? Like, did you understand why did we use the average velocity and not the maximum velocity here? So I hope you have,
Yes.
yeah, okay. So now, okay. So now from this, since mass flow rate is known, V average is basically m dot. So this will be m dot divided by rho times the area. Okay. And m dot is given to us. So how much is m dot? M dot is basically 0.01 kg per second. So let's do the calculation. So it's 0.01. This is kg per second. Density of water, you can assume it to be 1000. And area would be just the cross-sectional area of the pipe, which is pi by 4 times the diameter squared. Okay. This is density, which will be in kg per meter cube, of course. And this area would be in what? So this would be in meter squared. Okay, this gives us, so if you just do this, so the unit wise also it makes sense, because this will have an unit of meter per second, which is velocity. Okay, so now if you calculate, so I have done this a priori. If you do this calculation, like if you do this math and substitute, because the diameter is given, okay, how much is the diameter? So diameter is around what, 25 mm. So d is basically 25 into 10 to the power minus 3 meters. And if you substitute it here, you will get V max, I'm sorry, you'll get V average to be around 0.02 meters per second. Okay. However, Do we require V average? We don't require V average because in order to find the unknown pressure gradient, we required V max. Okay. Now tell me what is the relationship between V max and V average in case of a like this Hagen Poiseuille flow. Can you tell me from the U average how do we calculate the U max or V max?
Twice
Yeah,
of
exactly. So this is a very like famous result that Vmax for a Hagen. So remember this is only true for a Hagen possible flow. Okay, so the Vmax for a Hagen possible problem is just twice of V average, and this thus becomes to be equals to 0.04. Okay, so I would write here. So for Hagen possible problems, okay, for Hagen possible problem, the ratio of this Vmax by V average is 2. Now, can you tell me this ratio for a plain possible flow? Can you tell me what is the ratio of Vmax by V?
1.5.
Yeah, exactly.
1.
Exactly. It's 3/2 basically. So this is something that you need to understand. Okay, it's not always so the prefactor is not always 2, and it just depends on the physical nature of the flow. Okay, but for this case, this is 2. For this case, this is 2, and that's why we have substituted it as 2 into V average. So now it's known to us. Okay, now this Vmax is known. So if you put this Vmax here, if you just put you just put this Vmax here into this equation and you get dp by dz. Okay. Yeah, so that's the second part. So what is Vmax basically? So Vmax is calculated. This is Vmax. That's the first part of the problem. And in the second part, so Vmax is just what? It's just 1 upon 4 mu times dp dz into r squared, where this Vmax is just 0.04. You just substitute it. Mu for water is of the order of 10 to the power minus 3. I don't know exactly the value. It's just of the order of 10 to the power minus 3 Pascal second. Look into this value in the net, that what is the dynamic viscosity, because it's a physical property, right? So just see what is the dynamic viscosity of water at 27 degrees Celsius. And this is precisely the reason why temperature is given. That is simply because viscosity of fluids typically change with temperature. And can you tell me what's the nature? Like if we increase temperature, what happens to the viscosity of fluid? I mean that's the first question that arises, right? I mean this for this question it's fine. For this problem it's
decreases.
fine. Yeah, exactly. So the viscosity of fluids actually decreases with increasing temperature. However, this is not so for gases, because for gases like the viscosity increases, right? If I'm not wrong.
Yeah.
Yeah, exactly. Can you tell physically explain me why this is the case, that for fluids the viscosity decreases with temperature and for gases viscosity increases with temperature? Do you know? Yeah. Anyway, I'll tell you the reason. But for this problem, like you just need to evaluate this dp by dz, and this r is also given. This would be just d by 2. So if you just evaluate this dp by dz, you'll get some numerical answer, and I leave you the maths for you to figure out. Okay, this is something that you can do very easily. All right. Yeah, so my question was, so yeah, that's so I'm not interested in the final answer because you can anyway solve that. I'm more rather interested in anyway, I'll just let you know that this pressure gradient will, you can check this pressure gradient will come out to be 0.9113. Since this is gradient, it will be Pascal per meter. And if the length of the pipe is known, you can eventually calculate what will be that delta P that you need to maintain in order to get the desired mass flow rate, which is given. Okay, just check this, that you will get it to be around zero point 0.9 Pascal, sorry, yeah, zero point 0.9 Pascal per meter. Yeah, so the question was, so I think this is, you understood this very nicely, okay? So my question was, which is of course not related to this particular problem, but what I asked you is that why the viscosity of fluids means viscosity of liquids basically decreases with increasing temperature, and why viscosity of gases basically increases with increasing temperature. So that's the question. I will not answer directly the question now. You can let me know your answer in the previous class, but I'll give you an idea. So in fluids, viscosity is related to that cohesive forces which acts between the surface which is in like contact with the fluid and the fluid itself. However, in gases, the cohesive forces doesn't come into the picture, and there is something else that that basically occurs in gases. Okay, and these two are and these two are completely different physics, and that's why viscosities of liquids and gases show different trends when we increase or decrease temperature. Okay, so this is the idea behind this. I will not directly tell you the answer. You can look upon that in your like free time, and then you can let me know in the next class, or you can post it in the discussion forum, and I will check like discussion forum of this course, of course, and then I will let you know if that is correct or not. Okay, so again I would wait here for some time. I hope this problem is clear. And this is, of course, if it appears as a simpler problem, but again you need to think about this. That when we so the main crux of this problem is that when we calculate the mass flow rate, it is always associated. To remember, it is always associated with the average velocity and not the maximum velocity or something else. Because mass flow rate is always an average quantity, and it should not vary along the y direction. Okay, y direction or the r direction, which is basically the cross flow direction of the problem. All right. If this is clear, I will again wait for some time, and then we will begin with the next problem. And next problem is an important problem, and we will learn much more various physics that is associated with it when we go and solve this problem. Okay, but before starting the next problem, I'll again stop here for some time, and and like then we'll begin. So you can So I'll display the problem here. You can think about this problem. I'll display what to write. I'll just come in 1 or 2 minutes. I'll just fill my jug, and then I'll come and I will state the problem for you. We can think about it, how you will go ahead and solve this problem. The hint is that this problem now is not a 1D problem, as you can see. But the very nature of the problem will enable us to have some see if it's not a 1D problem, which of course if you think like you will see that it's of course not a 1D problem, but sometimes even if the problem is not 1D, we can have analytical results, and we will see though like how it is possible. I'll just come in 2-3 minutes. You can think about this problem. All right, guys. Sorry for the interruptions. So let's get started with the third problem. And of course, this is a long problem. So we'll just solve this problem very systematically. And this is something that we will see. This is the last problem for this session. But of course, it's a long problem, and it will of course take some time. So let's understand this. So I just call this problem as fluid dynamics of an extrusion process. So typically, as mechanical engineers or like chemical engineers or material engineers, you know what's an extrusion process is, right? So it's like it's like we want to. So as the name suggests, we want to move up. We want to get a particular uh, volume of fluid out of a certain system, and for that we apply certain mechanical forces or mechanical like stresses or something like that to just move that volume of fluid out of a structure. Okay, so this is, so for that we need to apply force, of course. So and this typically in so a material scientist would be very like he would be very much like more he can explain this in much more depth, but this is typically known as an extrusion process. We are not interested in what extrusion basically means technically, but we are more interested in understanding the fluid dynamics that happens inside an extrusion process. Okay, so when extrusion, so in a way of performing this extrusion is that you can put like fluid between two concentric cylinders, as you can see from this picture. So this blue shades is basically the fluid that is inside this cylinder, and then you rotate the cylinder with some known angular velocities which are basically given. So you rotate the two cylinders, so the inner cylinder rotates with some angular velocity omega 1 and the outer cylinder rotates with some angular velocity omega 2. However, in order to move the fluid out of the structure, this is not sufficient. Okay, the cylinder rotation will be there in, of course, so omega 1 and omega 2 can be of the same sense, or it can be of different senses as well, depending on what nature of substance or nature of substance that we desire. However, in order to move the fluid, we also apply an axial pressure gradient in this direction, in the z direction, as you can see, because the z direction will be along this dotted line in this picture. Okay, so from this problem, as you can see, the rotational velocity of the fluid, or sorry, the rotational velocity of the cylinder will move the fluid in the theta direction. Of course, this is basically because the rotational velocity is omega cross er, right, where r is basically the radius. Okay, so this will move the velocity in the theta direction, and the axial pressure gradient will move the fluid in the z direction. So this means the velocity profile of the fluid will now no longer be, so the velocity profile of the fluid will now no longer be an 1D velocity profile, and we will have velocities in two directions. So because of this pressure gradient, we will have a velocity in the z direction. That's why we will have this uz, which will be the velocity component in z direction. And because of the rotation of the cylinders, we will have velocity in the theta direction as well, which will basically be u theta. Now, if the cylinders are not, so if the cylinders are not perforated and they are solid cylinders, can you tell me, will we have a velocity in the r direction? This is the first question that I will ask. Like, based on your understanding of this problem, will we have a velocity in the r direction, or we should not have a velocity in the r direction, or what limits the velocity, or what limits the flow in r direction in this case if the cylinders are solid and they are not perforated? Or what is that condition that tells us that there should not be a velocity in the radial direction? That is what I am asking. Can you just give us an idea?
Flow is confined.
Yeah,
So
exactly. But exactly, the flow is confined, and technically, that condition is known as no penetration condition. Okay, so the fluid cannot penetrate. So at r equals to, let's say at r equals to a and at r equals to b, ur always has to be 0 because this is the no penetration boundary condition. Okay, very nice. However, we will have two velocity components. As you can see, this is basically the u theta and the uz direction, and we will basically solve for this velocity profile. Okay, but in order to have analytical solutions to this, I'm assuming that the flow is steady, it is axisymmetric. I'll ask you what axisymmetric basically means, and it is fully developed. Okay, so this is the assumption that I have given to you, and then our objective again is to find out the velocity field in the liquid. Okay, so let's get started, and let's get started with this problem. Of course, I would start off by explaining the assumptions as we do. And please let me know if you have any doubt, but this is of course an important problem. As you will see, we will also learn certain mathematical equations that we perhaps we have not seen it before. And yeah, so this is the idea, okay? So I'll start off by explaining the assumptions. So the first assumption, as we all know, is the steady flow assumption, which means that if you perform any derivative or with time, this would be 0. This is something that we know. Can you tell me what is the meaning of this axisymmetric boundary condition here? What is, so physically and mathematically, what does axisymmetry means in this problem? Or in other words, what does axisymmetry means in cylindrical coordinates?
u at r equal to u at minus r.
U at
something.
R, yeah, okay. So what you are saying that U at R means this A or something else.
Radial location. I mean, if region is at center line. I mean,
Okay,
axis is at center line.
okay. And that what is R then?
Radial distance
Okay,
from
this
center.
means this distance. That's what you are saying.
Yeah.
But then why do we have a minus R here? Because there is no negative radius, right? So R starts from 0, right? Okay, that's fine. So that actually not is axisymmetry. Yeah. Do you want to tell something else? Okay, I will let you know. Okay, perhaps you might not have gone through this axisymmetric thing. That's not a big deal. I'll explain you what axisymmetry means. So see, axisymmetry means that at any point, if we move around these cylinders, the flow field would basically remain the same. That means that basically means that if I take a gradient of any variable in the theta direction, that will not change. Okay, this is basically the meaning of axisymmetry. Or in other words, if I move around the cylinder, that let's say I move around, so for your simplicity, let's try to think in something like this. If I move around this, so this is the fluid region, right? This is basically the fluid region. So in the fluid region, if I now move around this fluid region, let's say I'm at this point and I have a velocity profile, which is let's say u theta, let's say u. And if I now move around this, moving around this means I'm revolving around the z axis. Okay. If I now come instead of this point, I now come at this point. So axisymmetry means that the fluid velocity at this and this point would be same, which means that the variables are independent of theta and its gradient. This is actually the meaning of axisymmetry. Okay. So I'll write down. I hope this is clear. Is the meaning of axisymmetry clear? This is in uh, this is this meaning of axisymmetry is actually a function of what coordinate system do we follow. There is nothing axisymmetric in Cartesian coordinate system. The definition of axisymmetric in cylindrical coordinate system is that the variables are independent of theta or its gradient, and the variable of axisymmetry in spherical coordinate system is also different. This is I will let you know what axisymmetric means in spherical coordinate in some later time. But did you understand what axisymmetry means in cylindrical coordinate? Like, did you get the point?
Yes, yes.
Okay, okay. So I'll write it down. So it means that all variables are independent of theta and its derivatives, like del theta or del square theta by so or del square, yeah, or something like this. Okay, so this means this is equals to 0 and this is equals to 0. So this is the meaning of axisymmetry. So now I think you got what's the meaning of steady flow. I think you got what's the meaning of axisymmetry. Of course, this axisymmetric, this is in reference to the cylindrical coordinate system. This in reference to cylindrical systems. Okay. And we are also assuming that there is no body forces. There is no body forces. We are assuming that there is no body forces in the fluid. This is also an assumption. And fourth, we'll also assume one more assumption, which is basically the fully developed condition, which again that the fully developed condition states that so any derivative of the velocity field with respect to the z direction is 0. I think this is perhaps you have seen repeatedly. Okay, so these are the assumptions as I have said. Perhaps this axisymmetric assumption is new to you, but I think this steady flow and this fully developed assumptions are something that we have done repeatedly. Okay, so based on these assumptions, let's now start our problem by writing the continuity equation. So now, since this is a cylindrical problem, and since as you have seen also in the Hagen possible flow, we need to now convert our system into the cylindrical geometry. The continuity equation in cylindrical coordinate basically looks something like this. So it is 1 by r del r of r ur plus 1 by r del u theta by del theta plus del uz by del z equals to 0. All right. So this is the continuity equation. Now you guys tell me, okay, how do we apply the assumptions in the continuity equations now? First of all, can you tell me what will happen to this term?
0.
Yeah, 0. Why?
UR is 0.
UR is 0. That's the no penetration condition. Okay, so this term is 0, which means the no penetration boundary condition. Okay. Can you now tell me what will happen to this term?
0. Axisymmetric condition.
Axisymmetric. Yeah. So this is 0 again because of the axisymmetric condition. And this is 0 again because of the fully developed condition.
Yeah.
So this means, so what does this mean? So this means that the continuity is trivially satisfied in by using the so the continuity equation is trivially satisfied by using the above mentioned assumptions. Okay, this is what basically will mean here, that continuity equation is trivially satisfied. All right. However, here is now the catch. So I hope this everything is clear up to this point. So now here is the main thing that that differentiates this problem with the other problem. Now we know UR is equals to 0, that is from the no penetration boundary condition, but there will be a non-zero U theta and there will be a non-zero UZ. Okay, I hope this is fine. That there will be a non-zero U theta and there will be a non-zero U theta, and this makes, as I have said, as I have, so these two will be of course not equals to 0, and this makes the problem to be two-dimensional in nature. Okay, so this makes the problem the 2D problem. So we will now start off very systematically. We will now start off by applying the Navier-Stokes equation in the theta direction and see, let's see what do we get. Let's see if you can solve this problem or not. We'll start off by applying the Navier-Stokes equation in the theta direction. Okay. So you don't need to remember explicitly the equation in cylindrical coordinate. I will write that for you. So in theta direction, so in theta direction, the Navier-Stokes equation looks basically something like this. Okay. So it is, so the steady term is basically this plus UR del U theta by del R plus U theta by R times del U theta by del theta plus UR, okay, plus UZ times del U theta by del Z. This is, so you don't need to remember this explicitly. In your exam, if this comes, either this equation should be given to you if your exam is a subjective exam, or like this, or like if for your practice problems, like you will have these equations in any in any standard fluid dynamics book. Okay, so this is the inertia term, and the pressure gradient term is basically something like this. So it is 1 by r del p by del theta plus mu, which is the dynamic viscosity, times 1 upon r into, I'll write the other terms here, del r of r times del u theta by del r. Okay, plus, so it's a long equation, bear with me, plus it is 1 by r square times del square u theta by del theta squared plus del square u theta by del z square, uh, plus there are two more terms, which is 2 by r squared times del ur by del theta minus u theta by r squared. Yes, okay. So yeah, so that's a long equation as you can see. But now let's use the simplifications now. So this term again would be 0 because of the fact that the flow is steady. This term is 0 because of the no penetration boundary condition. This term is 0 again because of the axisymmetric condition. This is again 0. Okay. And in the theta direction, there is no pressure gradient, which means, okay, 1 second. This term is also 0. Can you tell me why this term is 0? Del u theta by del z. I have said
U theta only function of R.
Correct, yeah. U theta is a function of r, that is correct, and also because of the fully developed condition. So the fully
Yeah.
developed condition implies that U theta is a function of r only, and that's why this is 0. There is no applied pressure gradient in the theta direction. Remember, the pressure gradient is only applied in the z direction and not in the theta direction, which means this is 0. This is 0, fine. This term would not be 0 because U theta is a function of r. Okay, this term would be there. And then what happens is this term is 0 because of the axisymmetric condition. This term is 0 again because del u theta by del z is 0. And this term is of course 0 because of the no penetration condition. So let's write the remaining terms. Let's write the remaining terms. So what do we have? We have this term. We have this term basically. And yeah, and this term. Yeah, we just have this term. So let's write this. So we have, so what we have? We have mu times of 1 upon r into, since u, as you said, u theta is just a function of r, we can remove the we can remove this pd, I mean this partial sign into a complete derivative, which becomes pdr of r times du theta by r minus of u theta by r squared. Okay, this equals to 0. And since mu is not equal to 0, we can write 1 by r ddr of r times du theta by dr minus u theta by r squared. Okay, I hope this is clear. It's just the math that we are doing. Yeah. Now, if I expand this using the chain rule, as you know, this will simply turn out to be what? This will simply turn, I'll just expand this. So if I do this, let's apply the chain rule here. It will just be what? It will be du theta by dr, okay, plus r times t square u theta by dr square. We are just applying the chain rule here for this term. Okay, derivative of the first multiplied by keeping the second constant plus keeping the first constant into derivative of the second term. Okay, and there is a 1 by r that is already multiplied. All right, and then we have this u theta by r squared equals to 0. Okay, now let's do one thing. Let's first include this 1 by r here, and let's see what do we get. So we get what? We get 1 by r du theta by dr plus d squared u theta by dr squared minus u theta by r squared. Now what we'll do is, in order to simplify this equation, let's do one thing. Let's multiply this entire equation by r squared. Okay, on the left hand side and right hand side. So if we do that and just rearrange certain terms, we will get something like this: r squared times d2 u theta by dr squared plus r times du theta by dr minus u theta is equals to 0. What we are doing is, as I repeat again, we are multiplying this entire equation by r squared and just rearranging these terms. I bring this term front, I bring this term here, and this term is always there. Okay, all right. These particular equations, that the equation that you get has a special name. Can you tell me what is this equation called? This particular equation bears a special name, and it is not so trivial. I don't know, like in mathematics, this equation has got a special name. Okay, can you tell me? This r square times d2 u theta by dr square plus r times du theta by dr minus u theta equals to 0, where u theta is just some dependent variable and r is the independent variable here. And this equation has got a special name in mathematics. Can you tell me? All right. I will like tell you the hint. So, okay. So can you tell me what is the dimension of u theta? That is this term. What is the dimension? What is the dimension of velocity? It's meter per second, right? I hope you are on this. So it's meter per second, right? All right. Now can you tell me can you tell me what is the dimension of this term? d2, like I'm asking what is the dimension of this d2 u theta by dr squared. So if I'm not wrong, dimension of u theta will still be meter per second, and since there is a derivative squared, it will be meter squared. And then there is a multiplication with this r squared, which is basically this term. Okay, which is basically this term, and from here we'll get a meter squared. Okay, and this means that the dimension of the entire term, which is this r squared type d2 u theta by dr squared, is just meter per second. So similarly, if you do the same exercise for here, the dimension of this term would also come out to be meter per second. And since all these terms here's the same dimension, that's why this equation, I write it as equation 1, this is often referred as equidimensional equation. Okay, this is often referred as equidimensional equation. And this is the special name of this equation. Now, since this equation has got a special name, there is a way of solving this equation. Do you know how do we solve this equation? Because ultimately, we need to obtain this u theta, right? Ultimately, we just need to obtain this u theta. So can you tell me how do we solve this? How do we solve this equation? Do you have any idea how we apply? How do we solve this equidimensional equation? I mean, again, this is not so trivial, and I understand this is new to you, but you will know, like from now on, like at least you will know that if you get equation of this sort, this is how, this is known as the equidimensional equation, and this is how we solve equidimensional equations. Okay, so I'll give you the idea. So what we do is we assume. So let's try to solve this equation 1. So for this we'll assume u theta of the form some r power k, where k is not known to us, where this k is unknown, and we will actually solve for this k. Okay, where this k is basically unknown. Okay, and we can do this, we can basically do this because this equation is equidimensional in nature. Okay, that's why actually we can assume this r to be of this certain form. Okay, now what we'll do is we'll substitute this. So we'll substitute this in equation 1. For that we need to evaluate certain things. So if u theta is r power k, then what do we get? Let's evaluate these terms. 1 second. Let's evaluate these terms. Okay, so d2 u theta by dr squared, this becomes what? This becomes k into k minus 1 if you do the algebra, into r power k minus 2. That is simply because du theta by dr would be k times r power k minus 1, and if you take one more derivative, you will end up getting this k times k minus 2 times r power k minus 1. Okay. Similarly, in the same sense, as I have already said, du theta by dr, this would be just k times r power k minus 1. Okay. So now we know this thing. So we know what is u theta, we know its second derivative, and we know its third derivative. So I'll name this as 1a. I would name these two as 1b and 1c. All right. So what we will do is we'll substitute 1a, 1b, and 1c in equation 1, which is basically our equidimensional equation, which is basically this. And let's see what do we get. So we have r squared. So what we have? We have r squared times the second derivative, which is basically this. Okay. This is k into k minus 1 times r power k minus 2. And then we have this term, r times the first derivative. Okay, let's see what we get. So we have r times k into r power k minus 1. Okay, and then we have u theta, I think, minus of u theta, which is basically this. Minus of u theta is just r power k. And we have this equals to 0. And let's now simplify it. So if we simplify it, let's see what we get. We have k into k minus 1, r to the power minus 2, and this here plus 2 will give us just r power k, of course, plus this will again give us what? This will again give us k into, this will again give us k into r power k if you simplify this. That is because minus 1 and here is 1 plus 1, and this becomes r power k. Okay, now since we have assumed u theta to be of r power k, r power k cannot be equals to 0, right? Because if r power k itself becomes equals to 0, then there is no point in solving this u theta because the cylinders are rotating, right? So it's impossible that r power k can be equals to 0. Okay, this means that since this cannot be equals to 0, we can take r power k common of this equation and we'll just end up getting k into k minus 1 plus k minus 1 equals to 0. And since this term cannot be equals to 0, this term cannot be equals to 0, then we just end up getting k into k minus 1 plus k minus 1 equals to 0. Okay, and if I now solve for this, what do we get? Let's say k square minus k plus k minus 1 equals to 0. This becomes cancelled and we just end up getting k squared equals to 1, which gives us k to be equal to plus and minus of 1, right? So we have eventually solved out what will be the value of k, and in fact this should be true, right? Because that is simply because, as you can see, this is the second order. This is a so what is this? This is the second order ODE, right? The problem is that even if it's a second order ODE, it's a ODE with variable coefficient, which is R. And that's why we cannot directly apply our traditional technique of solving it. And that's why this is a way of solving equidimensional problem. Now, this k has to have two roots because it's a second order. And that's why we are getting k to be equal to plus and minus 1. So I hope this procedure is clear. This is how we solve an equidimensional equation. So now, since we got k to be equal to plus and minus 1, what will be u theta? So we assume u theta to be of r power k, and that's why this u theta would now become what? So it will now become a1 times r power 1 plus a2 by r power minus 1, and this would just becomes a2 by r, because there has to be this linear combination of these two terms. Okay, so far so good. So this is, let's say I'll name it equation. So did you understand how do we solve the equidimensional equation? Or do you have any doubts? Like, I would wait here for like 1 or 2 minutes. If you have any doubts, you can like point it out. All right. I believe you don't have any doubts. So now tell me, how do we get this A1 or A2? How do we get this A1 or A2? Any idea or any suggestions, like how do we get this A1 or A2?
Boundary condition.
Yeah, boundary conditions. So we apply the boundary conditions. So the first boundary condition suggests that so let's see the figure. What's the first boundary condition? So the first boundary condition suggests that the velocity field in the theta direction at r equals to a is just omega cross r1, right? Which is basically omega times a. Okay. So I hope this is clear. See, this is very like trivial, right? I hope you have understood why it becomes omega times a in the theta direction. See, the vorticity or the angular velocity. So what is the direction of this angular velocity? See, the direction of this angular velocity, if we apply the right hand thumb rule is in the z direction, and the radius is in the r direction, which means this just becomes, so vectorically it becomes omega, which is the magnitude, into it becomes z, it's the magnitude into z, okay, cross the r direction, which is r, and z cross r is theta, and that's why it's just omega times a. So I hope this is clear. I would write it down for you to be like absolutely clear why it becomes just omega a. So what I was saying is that at 1, so this u theta, so this u theta is 1. So u theta is basically omega, which is the omega is basically the angular velocity, cross r. R is again the radius, and if I write down its magnitude, it becomes omega 1. The direction of this vorticity and the angular velocity, if we follow the right hand thumb rule, is in the z direction. That's why this becomes Ez. And at r equals to 1, this r becomes a times the radial vector, which is basically a times er, where er hat is the radial vector. Okay, and this Ez cross er is basically e theta. That is, you can verify it. This is just the cross thumb. I mean, this is the cross product that we do. Okay, and that's why this becomes omega 1. This is of course a vector into a into e theta. And see, since we are explicitly interested in the theta direction only, that is, we are solving this. That means we are solving this all sets. This uh, we are solving the Navier-Stokes equation in the theta direction only. We can rest assured, we can just say that the magnitude of u theta will be just omega 1 into a. I hope this is clear to everyone. How did we get this u theta to be equals to omega 1a? Okay. In the same spirit, at so this is happening at r1 equals to a. Okay. In the same spirit, if we apply at r1 equals to b, you will get, so let's write this is u theta. How do you write? Okay, so at r1 equals to b, u theta would just be omega 2 times b. Let's write this way. It is omega 2 times b. Again, just apply the same logic here. Okay, just apply the same logic here for the outer cylinder. Okay, so this becomes u theta equals to omega times b. So that's it. We just require two boundary conditions, and we have these two boundary conditions. Let's name this as equations 2a and 2b. Is this clear to everyone up to this point? How u theta becomes, how the magnitude of the u theta becomes omega 1a at r equals to a, and how the magnitude of u theta becomes omega 2 times b at r equals to b. Is this clear? Like, this has to be clear, okay? Yeah, go ahead.
Clear.
Yeah, okay, good. Okay, so now let's just apply this. Let's just go ahead and apply this here. So what do we have? We have u theta equals to a1 times of r. So at, let's now apply this at r equals to a. Okay, so this becomes u theta at a. This becomes a1 times a plus a2 by a, and u theta at r equals to a becomes, it's just omega 1 times a, and this becomes a1 times a plus a2 times a. Okay, this is one equation. Let's say we are writing this as 3a. Similarly, if we apply this at r equals to b, what we will get is, we will get u theta at b would be a1 times b plus a2 times b, and u theta at b is just omega 2 times b, where omega 2 is basically the rotational velocity of the outer cylinder, and this just becomes a1 times b plus a2 times b, and this becomes equation 3b. Now again, we have two unknowns, which are basically this a1 and a2, and we have two equations, which is basically 3a and 3b. Okay, so again I repeat, we have two unknowns, basically these constants a1 and a2. By the way, why can you tell me the condition? Like, I mean, you guys know that this condition that we wrote here, is basically the no slip condition only, and it's nothing else. So these two are basically the no slip conditions at the interfaces a and b. It's the no slip condition. I just want to point it out. And yeah, so now since we have two equations and two unknowns, a1 and a2, you can go ahead and solve this, and I would not do this here now because of the interest of time. You can go ahead and solve this, and what you will get is, you will get a1 to be of, you can verify this, you will get a1 to be something like this. It is omega 1 minus b squared by b squared minus a squared, okay, into omega 1 minus omega 2. So this is just math, two equations and two unknown. You can just solve it by yourself. And this a2, basically you will get it to be something like this. It is a squared b squared into omega 1 minus omega 2 divided by b squared minus a squared. Okay, so these are the constants that we were essentially seeking for. Again, I would like stress that we just need to solve, to evaluate this a1 and a2. We just need to solve this equation 3a and 3b, and this a1 and a2 basically comes something like this. Okay, so this means the total velocity field u theta, which is a function of r, of course, will come out to be, so it is what? It is a1, so u theta is what? U theta is basically this. It is just a1 times r plus a2 by r. Okay, so if you substitute the values of a1 and a2, which are basically this, okay, you will get u theta to be omega 1 minus So you just substitute the values, you'll get u theta to be omega 1 minus b squared by b squared minus of a squared into omega 1 minus omega 2. Okay, there is an r multiplied by it, so this becomes equals to r plus 1 by r times of a squared b squared by b squared minus a squared into omega 1 minus omega 2. Okay, so this is the u theta that we are essentially seeking for. But so this is u theta basically. Okay, this is basically u theta that we seek for. But this we are not done yet, because we are not done yet because there is also an applied pressure gradient in the z direction, as you like as you might recall, because the pressure gradient was applied in the z direction. Okay, so we'll quickly do this. So now can you tell me, in order to find the z direction velocity, what do we need to do? That is basically because we will now also have uz of r, and can you now tell me what do we need to do in order to calculate this z direction velocity?
Z direction momentum.
Exactly, z direction momentum. So we just need to apply Navier-Stokes equation. So I'll do this, and then I will stop at the end for getting for like if you have any comments or doubts. So we'll just apply Navier-Stokes equation in the z direction. This is relatively simple with respect to the theta direction, because if you apply in the z direction, I will not write the entire z direction, because we have seen this multiple times. So what you do is write the entire z direction momentum equation, invoke all the assumptions, and finally you will get something like this. Okay, this would be minus dp dz plus mu times 1 by r into ddr of r times duz by dr. Okay, and this is equals to 0, where this dp dz, remember this dp dz is known, and this is the applied pressure gradient. Okay, let's, for simplicity, let us consider this dp dz is just some g, which is basically known to us. Okay, this is known. And then let's just solve this problem. This is something that you did multiple times. Okay. 1 second. So this is something that you guys did. So let's quickly just solve this problem. So dz is, so minus of dz we are considering it as g, which means this simplifies to 1 by r ddr of r times duz by dr. Okay, is equals to, this becomes what? So let's do one thing. Let's take the minus sign out of this. So there's a minus sign here, or let's put this minus sign. What do we do? Let's not do this. Let's just take this total term as g, and then when we move this g to the other side, it becomes what? It becomes minus g upon mu, and let's now integrate this. So this is similar, this is familiar territory, right? You know what to do from here. So we need to integrate this with respect to r. So we need to integrate with respect to r, and if you do this, what we will get is, the first time we'll get this as ddr. Okay, so what we get? We get r times ddr of uz. Just integrate this with respect to r. Okay, you get r times ddr of uz, and this becomes minus g by 2 mu into r squared. The reason behind is that this r will basically move to the other side, and that's why this becomes r squared by 2 plus one constant. Let's now name this constant in b1, and then what we'll do is we'll divide the entire equation by 1 by r, which becomes duz by dr, and this becomes minus g by 2 mu into r plus b1 by r. And now again what we do is we integrate with respect to r. Okay, we integrate with respect to r, and what we get is we get du. Okay. If we integrate this with respect to r, we get uz as a function of r, and this becomes what? This becomes so r. So did I do it correctly? Yeah. So okay, this becomes minus g by 2 mu. There is an r here, so this becomes r squared by 2 plus b1. So integration of b1 by r is just b1 ln r, as you know, plus b2. Okay. All right. Okay, so let's simplify this. So what do we get is uj as a function of r is just what? It's just minus g upon 4 mu times r squared plus b1 times ln r plus b2. Okay, so this is the z direction velocity profile. This is the z direction velocity profile that we got by solving the z direction momentum equation, as you have rightly pointed out. All right. Okay. So now tell me, so if this is clear, that this is just mathematics, okay? You guys know how to. So what we did is we applied the Navier-Stokes equation in z direction by invoking all the assumptions. We just end up with, so as you know, we'll just end up getting a balance between the viscous term and the pressure gradient term, as you have saw. And if we just integrate this, of course, in cylindrical coordinate system, if we integrate this, we end up getting certain, so we just end up getting this term, okay? Now, can you tell me what will now be the boundary condition for uz at r equal to a and r equal to b? That is very important, okay? Because we need two boundary conditions, right? In order to evaluate this b1 and b2. So can you tell me?
0.
Yeah, exactly, exactly. That's very nice. So at r equals to a, uz at r equals to a is 0. Why? This is because at r equals to a, the cylinders are just rotating in the theta direction, right? So this means that a fluid layer that is adhering to that surface will just be 0. Okay, sorry, that means the fluid layer adhering to the surface will have a zero velocity in the z direction. It will just possess a non-zero u theta velocity. This is again due to the no slip boundary condition. Okay, and you have to be very clear with this boundary condition. And I'm happy that you could answer that. So uj at r equals to a 0. Similar physics is also applied at r equals to b. That is uj at r equals to b will also be equals to 0. I'll again repeat because this is very important. I'll repeat what I said. So what I said is that the z direction velocity at these two interfaces, the z direction velocity at the interface of the smaller cylinder and the larger cylinder is 0 solely because of the fact that there is this no slip boundary condition, due to which the fluid layer that is attached to this uh, interface of the smaller cylinder and also the bigger cylinder just possess a u theta velocity, which is again the no slip boundary condition. So if I just draw, for instance, if I just draw the uz velocity profile, the uz velocities at this point and this point would be 0. And the fluid would only possess then u theta velocity here. Okay. However, in the interim, that is in between these sections, the fluid would also possess a z direction velocity and also a theta direction velocity. This is something that you need to appreciate when we are actually solving this problem. Okay. So again, just do this math. Just substitute these boundary conditions here. I will not do this just because this is just repetition. What I would say is so this constants b1 and b2 just comes out to be g by 4 mu times of a squared minus b squared into ln a minus ln b. Just do this math by yourself. Just substitute these two boundary conditions in the sequence to get the constants b1 and b2. That's it. And b2 would be just g upon 4 mu. This comes out to be a squared plus a squared minus b squared by ln of a minus ln of b, okay, into ln a. So that's it. So these are the constants b1 and b2 that we are essentially looking for this problem. And if b1 and b2 is known, we can just substitute them in the uz velocity. So I'll just name this equation. So this equation is what? This equation will write it as equation 4. This will write it as equation 4. Okay. And this two will be 4a and 4b. So just substitute 4a and 4b to get the entire z direction velocity profile. Okay. And yeah, these are the two constants. All right, guys. I would stop here for some time now. If you have any doubts in solving, how did we solve this, so if you have any doubt in solving how this problem, the entire problem, you are free to unmute yourself and you can speak. In the next class, what we will do is we'll not carry forward now because we have done a lot of sums today. In the next class, I will show you some special cases of this solution. Okay, special cases means that what happens if one cylinder stops and the other cylinder rotates, or vice versa, or what happens when the angular velocity of one cylinder becomes exactly equal to the angular velocity of the other. And we'll look into some special cases of this problem. But this is a generalized case where we have considered the velocity to be some omega 1 and some omega 2. Okay, so I'll stop my teaching here for this session. If you have any doubts, you can unmute yourself and speak out. Or else, in the next class, we will again revisit this problem again. I'll let you, since it's a long problem, I'll let you like go. I'll recapitulate the steps once, and then again we will look into some special cases here. Okay, and again after like looking into the problem, we'll move ahead further with the other sets of discussions that we plan to do in the next week. All right, guys. If you have any doubt, please speak out, or else like we would call it a day here, and we'll meet next week. In the meantime, like I will share you these lecture notes in the course website, and you can easily access them uh, when whenever you are required. Okay. So I hope you enjoyed I mean solving this problem, because this was much of an involving problem, and yeah. All right, guys. If you don't have any doubts, I would end the meeting now. Thank you for joining this week session. I hope you have learned something new here. For instance, the equidimensional equation and so on and so forth. How to solve an equidimensional equation. The UZ part was rather simpler because we have seen it multiple times in how to solve this kind of geometries in the Z direction. But the theta direction, I hope it was a new like concept that we saw. Nevertheless, like we will see, as I have said, we will see certain special cases of this problem in the next class. With this, I would call it a day, and I believe you don't have any doubts now. If you have any doubts in the meantime, you can always post it in the discussion forum, and we will, of course, will either me or the course instructor and the tutor will address this doubts whenever like they are feasible to address. With this, I'll stop this now. I would end the meeting. Thank you very much for joining. I'm ending the meeting now.